Let me recall what we did as a fundamental theorem of line integrals. What was there that if you have C is a contour and F is analytic in domain D, and also C has to be in a contour in T with initial point Z naught and let its terminal point of the contour be Z1. Then, according to the fundamental theorem of this line integral, we had the value of this integral derivative of fz dz is given as the value of the function at the initial point minus at the terminal point minus at the initial point. Now, here we have a remarkable direction that will be clear in today's lecture. But let me first, if C is contour, if C is closed contour, then what happens in case of closed contour? You have this initial and terminal point to be same, and that means the right hand side in this above equality will be 0. So then the value of the integral over this closed in contour dz is equal to 0. So this is the way. Now the question is, instead of the derivative of function here, what Cauchy's theorem tries to answer that whether the same thing holds for fz or not. We are interested in knowing that whether this thing is equal to 0 or not instead of taking 0. But if we want to take benefit of this fundamental theorem of line integrals, then the benefit will come provided there exists function f, capital F, whose derivative is equal to f. So that we in the inside this integral, instead of small f, we can put capital F, so that I can write this to be so that then we can apply this fundamental theorem of line integrals. But the question is the existence of this such f, and we have to be very careful that existence of such f depends upon the kind of domain that we are choosing. We have to further give some classifications, give some types of the domains, and in certain types of the domains such an f exists, and this capital F, if it exists, is called the antiderivative or the primitive of this small f. This is called, if such exists, it is called antiderivative of f, or it is called primitive of f. So the question reduces to the for what domains. That means it depends upon the domain. It doesn't depend upon f, just needs to be analytic. The kind of domain will decide whether the antiderivative exists or not. So let me first classify the domains. First, I'm going to tell you about a convex domain. Convex domain, a domain D in complex plane C is said to be a convex domain if for any 2 points Z1 and Z2 in D, the line segment joining these 2 points, Z1, Z2 lies in domain D. That means if you have a domain, it's said to be convex if you consider any 2 points in that domain, and if you consider the line within that domain, that line must also lie inside the domain D. And for example, if you consider this domain, annular domain here, look at that. That means this interior part of this smaller circle is not included. We have this region only. We have this part as this is the only domain part. Okay. Look at here. We have this thing that if we consider a point here and another point here, then the line segment joining these 2 points has to pass through this interior of this smaller circle, and but this interior of this smaller circle, this part here is not a part of the domain. So that means this is not a convex domain. This is not convex domain. And some of the examples that you can verify is that, for example, any disk, whether it is open or closed, with center and radius r, is a convex domain, but since we don't need to talk about closed, we are talking about domain, so it needs to be open, it's convex. You can verify it, it's not a difficult task to verify. You just have to see that any 2 points, line segment joining any 2 points inside this disk is again a another type of domain that we have to consider is about star-like domains. Star-like domains. What is a star-like domain? Star-like domain is a domain T in C is star-like. It is star-like with respect to some point in domain D if for every point in the domain D, the line segment joining point A, we have to fix A, and Z is again inside domain D. You can note the difference here. Here that every convex domain becomes a star-like domain, because by definition of convex domain, A and Z are both the points of D, and a convex domain says that any 2 points in D and the line segment joining them is again in domain D. So that means the first thing that you can note here that ends are star-like with respect to any point. They are यहाँ पर सिर्फ एक A point मैंने फिक्स किया कि एक के with respect star like होना चाहिए, but convex domains are star-like with respect to any of its points. Domains are star-like. They are star-like with respect to any of its points. But the other way it is not true. Let's look at this example. If we consider this, let me consider this slit plane. Just taking a different color. Let us consider this slit plane. I'm considering this slit plane here. Just a minute. We are not considering this part. This is not the part of that. Means I'm just considering C minus this line segment minus infinity 0. I'm considering this part. It's the star-like domain. If you take any point on the real axis here, but it is star-like only with respect to a point on the real axis, and you take any other point, then you can always join that point with respect to your point here. You can always take any point. You can always join. It's true, but it is star-like with respect to points on positive real axis only, because elsewhere they are not star-like. That's where you will have a trouble here, because if you choose any point here, look at this. And if you choose any point here, and then corresponding to this, so if you want to check whether it is star-like with respect to this green point, then definitely you will have a point here, so that the line segment joining these 2 points will cross this negative axis, which we have already removed, which is not a part of this. So it's a star-like domain with respect to any point, but it's not convex. It is quite obvious that it is not convex. This is not convex, but star-like. It is star-like with respect to every real number, every positive. And so this is the object of interest for us, where we will establish the existence of the antiderivative. We will consider more general domains which cover star-like also, but the proof that we will be doing today is for star-like domain, and with the help of star-like domain, we will do it for more general domains, that the domains which are known to be simply connected domains. So let me write it as existence of antiderivative, and the theorem that explains things is that, let me write, let f be analytic on a star-like domain, on a star-like domain D. And when I say that it is star-like, you just have to keep in mind that it's star-like with respect to some point. Then there exists an analytic function capital F on D, such that capital F of Z is equal to, derivative of capital F of Z is equal to F of Z for each Z in D. So this is, they are clearly saying that this the antiderivative of this analytic function exists on this domain D. Here you will get to know where we are using this star-like domain. So get this thing. So it is star-like domain, and so it is star-like with respect to some point. Let's suppose that it is star-like with respect to some point A. And now what we have to do, we have to define a function, and let me write that. Suppose D is star-like. It is star-like with respect to some point A in D. Then let me define a function capital F of Z as integral over the line segment A to Z, because this line segment is contained inside. If you have Z here, it is star-like with respect to A, so the line segment joining Z and A is always within this domain. So we can take this contour as Fz dz. Here is this function. And we will prove that this function is actually differentiable here, and its derivative comes out to be f of x. But the first thing that you may note here is that the derivative of, value of f at A is 0. Now, since what you say, this is a domain, it's an open set, and I'm taking a point Z here. So it is a Z is an interior point. If it is an interior point, I can always draw a disk, open disk around this Z, such that that disk is again within that domain. and it is of certain radius r. Okay, now I have to choose. I have to choose h such that z plus h is again this disk. Let me call this, this is the rotation dzr is again here. This is always possible because what you have to do to make sure that z plus h is in this disk, you have to make sure that modulus of h, mod of h is less than, because for z plus h to be in this disk, the distance of z and z plus h needs to be less than r. And what is the distance? Z plus z and z plus h, that is the mod of h. And then we have to select h so that mod of h is less than r. So when we say that I'm selecting h in such a way that this z plus h is in this disk, then that means mod of h is less than r. So let me choose a different. Let this be the point here. Let this be z plus h. Since disk is always a convex domain, so the line segment which joins z plus h to z is again inside it. Not only this, again we are using here the star likeness of this domain, because z plus h is the element of domain d and a, and the line segment which joins a to this z plus h will again be lying inside the domain d, because this is star like with respect to it. Now we have a triangle. Let me fix this orientation. It has to be anti-clockwise, and clearly this triangle T is inside the domain D. If this triangle is inside this domain D, I can use the Cauchy's theorem, Cauchy-Gorset theorem that we did yesterday for triangles. Therefore, by Cauchy-Gorset theorem, what you will have, you have this thing to be 0. But note that what is the boundary? What is the boundary of this triangle? Boundary of triangle is consists of 3 line segments. The line segment connecting A to Z, and the another line segment connecting Z to Z plus H, and the another line segment connecting Z plus H to A. So this is union of line segment A to Z, union Z to Z plus H, Z plus H, union Z plus H to A. So if that means I can write this integral as 0 equals to integral over. Now let me change. When I say that it is A to Z, I'm going to write, when I take the integral over line segment A to Z, I'm going to write line starts from A to Z in the form of the limits, indefinite integrals. It is f zeta d zeta plus another integral is from Z to Z plus H. It is f of zeta t zeta, and plus another integral with another part of this integral is over the line segment Z plus H to A. It is f zeta d zeta. What I'm going to change here, I'm going to keep A to Z as it is, and I'm going to write Z to Z plus H as it is, and here I'm going to reverse the order of these limits. What that will do, that will change the sign of this integral. It will be Z to Z plus H, and it is nothing but it is f of zeta t zeta. Now let me adjust the negative, because on the left hand side you have 0. So what you will have, you bring this negative side to here, and this integral a to z part also to the left hand side. What you will have this thing, integral a to z plus h, f of zeta d zeta minus, you will have a to z f of zeta d zeta equals to integral z to z plus h f of zeta d zeta. By definition of capital F, what you note here, this the left hand side, the first part is the capital F of Z plus H. This is the definition of capital F, and it is F of Z is equal to integral Z to Z plus H, F of zeta d zeta. This implies I am going to divide it by H also. I will have Fz plus H minus F of Z upon H minus F of Z. This is the uh, idea to show that when H goes to 0, this limit must be 0. So the right hand side now you reduces to 1 upon H integral Z, Z plus H, F of zeta d zeta minus F of Z. I'm going to write it this integral also. I'm going to write here because if I take it out, I don't have Z H with this. So if I take out, I have to multiply it with H, but I can write that H to be Z to Z plus H d zeta. This will give me H value. And now let me take the modulus of this expression. So modulus of this expression comes out to be Fz plus H minus F of Z H minus F of Z. It has to be, because when modulus enters the integral, it has to be less than or equal to 1 upon mod of H integral Z to Z plus H. Inside you will have F of zeta minus, you can write F of Z d zeta. So to make it sure that the left hand side goes to 0, I need to show that the right hand side of this inequality goes to 0. Let me analyze what is this right hand side. Now you have this function f is analytic, so f is continuous also. F is continuous also. When I say that it is continuous, so if we choose any epsilon bigger than 0, there will exist certain delta greater than 0, such that you will have this thing f of zeta minus f of z. It is continuous at z in particular, will be less than epsilon. Now we have this situation here. We have this disk here. When we are choosing this z and z plus h, we have the mod of h less than r. So what we can do, we can make sure that h is less than delta and this delta is less than r. Okay, because r is at our disposal, so we can choose r such that delta is less than equal to r. We don't have any trouble. So that mod of z minus z plus h, which is equal to mod of h, is less than delta. Because this is the selection of z, we have chosen this z to be in such a way that it lies within this domain. Or you can, why to take this to be, I don't think it has to be. I have to take this r to be smaller than this delta, so that we have this, because mod of h we are choosing to be less than r, so it will be ultimately less than delta. Look at the right hand side. Here, for z and z for h mod h less than delta, we will what we will have here. Hence, for mod h less than delta, we have this integral 1 upon mod h integral, where this is equal to z plus h mod of f of zeta minus f of z mod d zeta. This will be less than 1 upon mod of h. The integrand inside is less than epsilon. The integral that you have left is z to z plus h mod of d zeta, and the value of this integral is mod of h. It has to be equal to mod of h, and mod of h you will everything will be cancelled out here now, because mod h in the denominator and mod h in numerator will get cancelled out. You will have epsilon here. So finally, what you have now, you have Now we have for epsilon bigger than 0, we were able to find a delta bigger than 0 such that this expression fz plus h minus f of z upon h minus f of z is less than epsilon whenever mod of h is less than delta. But since epsilon is arbitrary, that means this goes to 0 as h goes to 0. You can conclude from here that the limit h goes to 0 of this fz plus h minus f of z over h exists, and this limit is nothing but the value of the f at z. But whenever the limit of this quotient exists, this limit is nothing but it is the derivative of the function at z, and this exists and is equal to the value of the function, small function f at z. So we have been able to prove this thing. Now z was chosen to be a point, arbitrary point in D, was arbitrary, and we found that at this arbitrary point, the derivative of the function capital F here that capital F derivative at each z is equal to small f of z for each z. And clearly, this is differentiable at each point of this domain D, hence it is an analytic function also. And this is the proof of this theorem. The immediate corollary that we have here is, let me write it as a corollary. What it says that if f is analytic on a star-like domain D, then for any closed contour C in D, the integral over of this function f dz. See, this is now the generalization, a more general version of the Cauchy-Korsaar theorem. Cauchy-Korsaar theorem was done only for, what you say, as triangles, but that was in arbitrary domains. Here you have a special type of domain where you can take arbitrary contours. How it is possible? Since you have star-like domains, so there exists, because of this theorem, there exists its antiderivative capital F such that its derivative is equal to f on t. Therefore, by a fundamental theorem of line integrals, now you refer to fundamental theorem of line integrals, what you have, line integrals, you have this thing, integral over any contour, closed contour C, f of z dz is equal to, you can write it as derivative of f of z dz, and it has to be f of initial point, f of terminal point of contour, terminal point minus f of initial point. But since it is a closed contour now, in case of closed contour, both the initial and terminal points are same, hence this difference has to be 0. And this is how you so this is actually the Cauchy theorem, but we will further generalize it, we will further extend it to more general domains, but step by step, first it is done for star-like domains. Okay, if you have any question, you may raise queries now. बोलिए.
हेलो सर.
हाँ जी बोलो.
सर आपने ना सेकंड यूनिट के दो टॉपिक के सर नोट्स नहीं शेयर किए हुए. एक सर कौशी
कौन कौन
हेडमैन
सा?
थ्योरम और एक यूनिक, एक है सर कौशी प्रोडक्ट और यूनिकनेस थ्योरम.
अच्छा, ठीक है, वो मैं भूल गया हूँ, वो मैं शेयर कर दूँगा. ठीक है,
ठीक है सर, थैंक यू.
ओके जी.